Uh, I'm just going to go through the motions. This is the final lecture that I'll be doing. Try to do a good job. On Wednesday, we have one of our own. So Alex Litzenberger will be doing a guest lecture. I recommend that all of you come here. Alex used to be a TA for the course. He was also twice, actually. And sometime during COVID, he decided to start a company. So he now has a company which is with offices in Wilkinsburg and elsewhere in the world. Got a bunch of employees, many millions of dollars of investment. And the stuff that they do basically builds off technologies that you might have learned in this classroom, some of the stuff we do for homeworks. And so it's a fantastic exercise on how a little bit of creative thinking and how putting things that you're very familiar with together to create products that people really need or should need. It's something that is well worth your time. Please attend. And he may also have projects that he's interested, that he's looking for people to work on. So you also have that. Let's continue with our final lecture. And today we're going to be talking about Boltzmann machines rather than Hopfield networks. But then just a quick recap. This is where we were last week. This is how we defined a Hopfield network. We had a network with loopy connections, where every neuron received an incoming field, which is the affine combination of the outputs of all the other neurons. And this was put through a threshold activation. So the way the network operated, if the sign of the field matched the sign of the output of the neuron, which is binary, 1 or -1, then the neuron didn't do anything. If the two signs did not match, it flipped. And we saw that this network would continue to evolve because of the loopy nature of the network. Anytime a neuron flipped, it would change the field at other neurons. So those neurons might flip, which could go back and change the field of the current neuron all over again, and which might then flip. So this evolution would continue until this energy term that we defined over here, which is the matrix inner product or the matrix norm of the current state of the network, which is basically the vector of the activations minus half this matrix norm. The network would continue to evolve until this converged to some local value. So here is how the computation would be performed. At each iteration, the network would be set to some value initially, and then you'd loop through the neurons and flip each neuron if it did not match the current field. You could do this in batch, all the neurons all at once, or go through the neurons one at a time. We saw that this network would evolve until this energy term actually hit a local minimum, regardless of where you started from. And because of this, if you set the local minima to be patterns that you wanted the network to remember, then you got content addressable memory. You could initialize the network with some degraded version of some pattern, and it's going to evolve, and it's going to recall the pattern that you stored. And this could be either just a noisy version of a pattern, or it could be an incomplete, in which case it would clean up the noise, or it could be an incomplete pattern, in which case it would perform pattern completion. So this was noisy pattern, initialize the network and let the entire network evolve. So there are two modes of operation. If I'm trying to clean up the noise, and if I'm trying to complete data, then I would have the network and some bits are already set. You know the upper portion of the image over here. There's no need for the upper portion of the image to change anymore. So you'd fix those bits and let only the remaining bits evolve. And it's going to recall the rest of the pattern. So these are the two modes of operation that we can think of. Now, the question is, how do you train this network to store specific patterns? Do you think we can use backprop to do this? Anyone? If I wanted to use backprop, how would I do it? Thoughts?
You have to think about the direction.
Keep talking. Yeah.
So conventional back propagation students, there is one coming from another direction, but
So here's what I could do, right? This is, even though it's loopy, I can actually think of the processing actually as something like this, right? That's your network without the self connections. And I can have this be an unrolled network where the same weights matrix happens between every two layers. This is exactly the same as this loopy network, is it not? Right? And so in this case, you can imagine that I can say that I can give it as targets patterns that I need to store, and I can give it as input noisy versions or incomplete versions of these targets, let the network evolve, and simply use back propagation to train the network parameters. So in fact, this actually looks very much like a denoising autoencoder, right? So the only difference being the depth. It's shared parameters, and the depth is technically infinite, but you could terminate it at any point, right? So yeah.
Professor, is the last point will minimize the energy function to back propagation?
You could minimize whatever. You could just minimize the KL divergence, right? The point is over here, the way we set it up, I'm giving it a noisy version, and I am as the input and the completed version as the output. Whereas if you were just trying to minimize the energy directly, then you're not thinking of it in terms of inputs and outputs. And so that's a more generic training operation. That's all, right? Anyway, so the Hopfield network can be trained to remember specific patterns. We saw that a network with n neurons can be designed to store up to n patterns, such that these n patterns are in energy wells. Yeah.
The number of times we unroll, is that a hyperparameter as well?
It's technically infinite, but you can stop it wherever the pattern stops changing, right? So that's up to you. That would be a hyperparameter for you. But then, if I'm thinking of it in terms of energy, here's a different way of thinking about it. You want to design the weights matrix such that the energy of the target patterns is minimized and the energy of other untargeted patterns is maximized. And so we can say that I want to minimize the sum of the energy of the target patterns minus the sum of the energy of the non-target patterns. So I want to define my weights such that in the energy contour during training, the energy at these target patterns is pulled down and the energy elsewhere is pushed up so that these target patterns become valleys. And so if I just use simple gradient descent, then we find that if I take based on how we define the energy, which is a matrix in a product, or the negative of a matrix in a product, the derivative of the energy with respect to the weights is going to have two terms. The first is the sum of the outer products of all of the patterns that we want to remember. The second is the sum of all the patterns we don't want to remember. The difference between these two is what we're trying to, is the gradient that we would need to follow to train the network. And of course, we don't need to, so this is minimizing the energy of the first term minimizes the energy of the target patterns. The second term maximizes the energy of the non-target patterns. We also saw that the second term can have an exponential, this second term would have an exponential number of terms. We don't need to necessarily consider all of these. Instead, we could just sort of pull up the regions just adjacent to the target patterns. So in which case, we just initialize the network at the valid memories we want to store, let it evolve a few steps, and then pull up the energy wherever it arrives. And that was what we wanted to do. So this was all very fine. Then there was this question. When I try to use this network to denoise something, I end up with a not clean recollection of the pattern. We have noise, right? So why is the recalled pattern not perfect? And we saw that this is because the network can actually have parasitic memories, these little energy wells, which If they're far away from the pattern that you're trying to recall, you're fine. But very often they will be close to the pattern that you're trying to recall. And that's when this network gets stuck in that point, and you get things like these little dots on the recall. And so that we would like to sort of give the network a chance to escape from these little energy wells, which means that as it evolves, if it arrives at some point, you want to nudge it out and then let it go back. And hopefully it will sort of come out of this little well and roll down to where it's supposed to go. And so to see how we could do that, we want to add some noise during evolution. And to see how we could do that, we went back and looked at spin glasses, where we saw that we can define an energy of the system for the spin glass, which is basically the product of the field at each dipole times the dipole value itself, the negative of that, right? And so that gives you an energy of the system. The system evolves to minimize this energy. But we also saw that the system is never really static in any configuration. In a real thermodynamic system, it's always going to be bouncing around between configurations. What changes is the probability with which it visits any particular state. And so this probability distribution is going to stabilize at some value. And what is the probability distribution? To define that, to determine that, we sort of looked at the math. We could define the Helmholtz free energy of the system, which is the sum of the average potential energy over all the states in the system, plus the entropy of the system, or Boltzmann constant times the entropy of the system, right? And so when the system evolves, it evolves to minimize this term. And if you actually work through the arithmetic, we find that at any temperature, if you just let the system sit and let it evolve, it's going to eventually arrive at a probability distribution over states, which was given by this Boltzmann distribution, which is where the probability of any state is proportional to the exponent of the negative of the energy of that state divided by the Boltzmann constant times the temperature, right? So note the dependence on T. At time T equals 0, if the temperature T is 0, this means that only the E of S, which is the smallest, is going to have any probability, because the comparisons, division by 0 is going to magnify the differences between probabilities, right? And so only the highest probability term is going to stay. Everything else will become zero, end up with zero probability. And so at absolute zero, the system is simply always going to stay in the lowest energy configuration that it can possibly get to. But as the temperature increases, the probability of bouncing around between states goes up. And so it's just going to be more likely to be found at this minimum energy state. But it can also has some non-zero likelihood of being at other states. So the evolution of the system is actually stochastic. And eventually the system is going to arrive at any temperature. If you let it be, it's going to arrive to some equilibrium. And at equilibrium, it's actually going to be visiting various states. And the probability of any state is given by is inversely related to its energy and also to the temperature, right? And the most likely state is the lowest energy state. We saw we can just implement the same idea in Hopfield networks. To do that, we recast the Hopfield network as a stochastic system. We said it's not going to deterministically go to the local minimum in energy. At any point, I'm going to redefine the system and say that the probability of that the system will be in any state is proportional to e raised to minus its energy. But then if I want to convert this network into this kind of a probabilistic system, I need some mechanism to make sure that it follows the same kind of dynamics that the spin glass does, right? And so to see how we could do that, we just consider the difference between the log probabilities of two states, which only differed in 1 bit. And when we worked through that, we found that the probability, if I fixed all the other bits, and if the probability distribution of the overstates was indeed a Boltzmann distribution, then we found that the probability that any bit would take the value 1 was simply given by the logistic computed at that neuron, where the argument to the logistic was the weight, the affine function of all the other neurons. And then this brought us back to something we're all very familiar with, which even goes back here, right? Which is that it's actually a probabilistic system. And now we find out where the notion of this logistic function that's very commonly used in networks came from. It actually starts off with considering these loopy networks, which are equivalents of thermodynamic systems. And once I unroll it, this actually becomes a standard staple for any deep neural network, right? So this was good. And it also showed us how we could redefine the regular Hopfield network as a stochastic system. Each neuron is now a stochastic unit with a binary state. I'm going to change it from -1, 1 to 0, 1, just because it's more convenient. You know, the logistic is defined between 0 and 1, right? Which can take a value 0 or 1 with a probability that depends on the local field. So I just switched it to 0, 1 just to stay with the logistic function, right? Not necessary. And so if I say that each neuron in the network takes the value 1 by some probability as opposed to deterministically, right? Earlier what we said was it was deterministic. If the field was negative, the neuron took the value -1 or 0. If the field was positive, it took the value 1. Here we are going to say it depends, it's going to do so with a probability. And the probability is given by this logistic function. So here's how this network would evolve. You're going to initialize all the neurons. Then you're going to cycle through the neurons. And at each neuron, you would compute the current field. Then you'd compute the logistic of that field, which is going to be this P of S equals 1. And then you'd flip a random coin with that probability for heads. If it turned out heads, you're going to set the value of the neuron to 1. Otherwise, you're going to set it to 0. Right? So, and we just we keep the neural network fixed, and we loop through the neurons and keep repeating this process. Now, observe how this differed from what we did when we were just thinking of it as a deterministic network. In the deterministic network, if the field was negative, the neuron became negative. That was it, right? Here it does so with a probability. And so that means that the network is never not going to converge to a fixed value, right? It's actually going to be stochastic because there's always a probability associated with the value of any neuron. Here is the actual operation of the neuron. I'm going to initialize the network with some pattern. Then I'm going to go through all of my neurons. At each neuron, I'm going to compute this probability P, and I'm going to choose the new value of the neuron according to a binomial distribution with that probability P. So the network is never static, right? So if the network is not static, how do I recall a pattern? When you're speaking of using content addressable memory, you want it to come to a deterministic value. And obviously that's not happening over here, right? So how can I recall the pattern? When do we stop? And what is the final state of the system? So let's look at this guy. What I can do is just let the network run for a very long time. And then at some point, I'm going to say over here, I believe the network has achieved equilibrium. From that point on, I can look at the state of the system for a large number of time steps, 5, 10, 15, 100, whatever. And then I'm going to get 100 different states. I can take the average of all of these guys and just apply a threshold function on this average. And that's going to give you the expected value, the thresholded expected value of the state. And that is most likely going to be the memory that you're trying to recall. So instead of getting a deterministic recall, you're looking at a large number of evolutions and taking the average. And that average is going to be your recall, right? And when you do so, you actually will find that because you're allowing the network to jiggle a bit, if you get stuck in a local minimum of this kind, it has a chance to just bounce out of it and go down the energy contour. And so now we can use this again for noisy pattern completion, initialize the entire network and let the entire network evolve, or complete incomplete patterns. I gave you half of a picture. I fixed the neurons whose values I already know, and I only let the rest of them evolve. So now here's where this notion of annealing also comes in. In a standard thermodynamic system, we have a temperature, right? And now, if I had some kind of a material, how do the theory is that if you want the material to be as hard as possible, you want it to have as much structure as possible. And so the way we do it is we raise the temperature, then we let it cool very slowly. If you don't wait long enough, if you stop at the wrong time, or if you cool the thing too fast, then it's going to end up at poor local minimum, whereas you want it to arrive at some kind of a global minimum, which is most stable, right? And so what you would do in a standard thermodynamic system is you'd raise the temperature and let it cool very, very slowly, so that at each temperature it arrives at some kind of a local, the stable configuration, and then takes a step down from there as the temperature goes down. So we want to implement the same concept here as well. In that now, instead of just defining the field as the weighted sum of all of the neurons, I can do it as 1 over T times the weighted sum of all of the neurons, where the T is a temperature parameter. When T is 1, this is the standard thing that we just saw, right? This was this guy. When T is 0, this is simply going to become when T is infinity, then all of them become 0, which means that all states are equally likely, right? Because every neuron has a probability now of being at 0.5, of being in either state 1 or state 0. So this becomes an uninformative system. It's not really recalling anything. At T is 0, this just basically becomes the Hopfield network. Only the most likely state is going to remain, right? And so you actually have the field quantifies the energy difference obtained by flipping the unit. If the difference is not large, so if I have a neuron, right, and it can take a value either 0 or 1, if the difference in the energy between when the neuron is 0 and when the neuron is 1 is not very much, then the probability that the neuron takes the value 0 or 1 is going to be close to 0.5, because both of them are almost equivalent. As this difference increases, then the probability of taking the value which results in the lower energy is going to keep increasing exponentially. So that's what this whole thing sets up, right? And T is a temperature parameter. Increasing it moves the probability of the bits towards 0.5. So if T is infinity, then Z becomes 0, right? And so which means that the probability for any bit being either 0 or 1 is 0.5. If T is 1, you get the traditional definition of field and energy. If T is 0, you get deterministic Hopfield behavior. And so if you're trying to do something like recalling these noisy patterns, and you want to escape these local minima, it makes sense to anneal. The concept of annealing actually was introduced in the machine learning literature by guys who were working on Boltzmann machines way back when, actually Hinton. So you initialize the network with the initial pattern, then set the temperature initially to some large value T0, and let the temperature reduce slowly towards a minimum value, which could be as low as 0 in steps. At each step, you sort of let the network evolve using that value of T, where each neuron is going to be set to either 0 or 1 by drawing from a binomial distribution whose value is given by this guy. Sigma is the logistic function. And the argument is 1 over T times the affine field at the neuron. So once the system has finally evolved to the lowest temperature, then you can just read off the last few steps of the evolution and take the average value as your prediction, right? So the whole thing kind of works. Now, so we saw what is the final state of the system and how do we recall a memory. When do we stop? How do you decide that the network is, we've run a sufficient number of iterations and we should either reduce the temperature or maybe take a reading. So for that, now we have to go back and look at the network as a probability distribution. The probability of each neuron is given by this conditional distribution, right? What is the overall probability of the entire set of neurons taking any particular configuration? That is simply going to be this term over here, right? So for any particular configuration, the probability of that configuration is given by this guy. And so what we would do is we would let the network evolve until this probability sort of converged. It's going to keep bouncing around, but as the network evolves, you're going to find that it's going towards, on average, lower and lower probabilities, and it's going to flatten out. When you say that this has come down sufficiently, the network is going to stop evolving. So stop when the running average of the log probability patterns stops increasing, or when the negative log probability stops decreasing, right? So all of this means is that, that when defined in this manner, the Hopfield network is a probability distribution over binary sequences. It's the Boltzmann distribution. The parameter of the distribution is the weights matrix W. And the conditional distribution of individual neurons in the network is a logistic function. And this entire thing is what we call a Boltzmann machine. So you're going to encounter the term Boltzmann machine often in the literature. This is what a Boltzmann machine is. The entire network model can also be viewed as a generative model. So now, if you train this network to store specific patterns, then you can use this to draw new examples. But what do we mean by storing specific patterns and drawing new examples? The content addressable memory concept doesn't extend to generative models, right? So how does one take a step away and make it a generative model? For that, we have to look at how you would train the network. Now, when I'm trying to train these networks to be content addressable memories, the number of patterns I would store is going to be small, right? But if I'm trying to make it a generative model, then I'm going to give it a large number of patterns to store, where all of the patterns belong to a specific class. So for instance, I could give you a large number of face images. And then I'm going to say, okay, just train these network parameters so that it remembers all face images. And then if everything goes right, you would expect that if I just randomly let the network run and settle at some local valley, the local valley is going to be that all of the valleys represent face-like images that can actually generate face images. So that's how it would generalize beyond the small number that you have taught it to store. So what this means is that you have to train the network to recall or remember or learn about a large number of training examples. Now, this network is a generative model. How do you do such a training? To train the network, you want to train it to assign a desired probability distribution to the states, meaning you'd get a large set of training inputs, like a large collection of face images, right? And you want the network to assign higher probability to images that it sees more frequently, lower probabilities to images that it sees less frequently, and no probability at all to things that don't belong to that class, right? And if you do this right, you want to hopefully it learns the distribution. So basically, if it's assigning higher probability to more frequent patterns and lower probability to less frequent patterns, what we are trying to perform is maximum likelihood training. You're training the network to maximize the likelihood of your data. Now, what is the probability of any individual pattern? The probability of any individual pattern is proportional to e raised to minus energy of the pattern. And the divisor over here, the term that is in the denominator, that's just the sum of this probability over all possible patterns. That is required to convert the whole thing to a probability distribution. Without the term in the denominator, it's not going to be a probability distribution. The terms are not going to sum to 1, right? It turns out that the guy in the denominator ends up being a bit of a tricky-ish, somewhat tricky when you want to apply maximum likelihood training. So let's go back and see. We all know what it meant to train these networks to just minimize the energy, right? We just said, I want to minimize the energy, average energy of all the patterns that I have in my training data. I want to maximize the energy of all of the patterns that are not in my training data. I may not necessarily maximize the energy of all of the patterns. I may maximize the energy of some of these patterns, and typically we'll just maximize the energy of patterns that are close to or some number of evolutions away from the patterns that we have in the training data. This is how we did the Hopfield network, right? Here, when I think of this as a Boltzmann machine, I'm going to try to maximize the log likelihood of all of the data that I do have. This looks like an entirely different principle, right? How does it work out? So the log, if I look at this equation over here, the log of the probability of any pattern S, which is log of P of S, is going to be minus of E of S minus the log of this term over here, right? And the minus of E of S is simply the weighted sum of the values of the bits on either side of each connection. And the denominator term is going to be, the second term is going to be the log of this guy here, which is the sum over all possible states, all possible settings of the neurons of e raised to the field at each neuron for each of these configurations, right? So this is the denominator term is the sum over all states S prime. By state, I mean a particular configuration of the neurons of e raised to the sum over all pairs of neurons within the network of the weighted sum of the values of the bits on either side of each connection for that particular arrangement S prime, right? So given this, now if I take a log, what does it look like? The log of it is going to have a first term, which is the summation over all pairs of, this is for any particular S, right? So log of P of S is going to be the weighted sum of the products of the pairs of bits. And the second term is, this is for the particular target pattern S, and this is for all possible states. It's a minus of log of the sum over all possible states of the exponent of, it's basically the first term, but summed over all possible states, right? And so now, if I want to take the average log likelihood of my training data, I'm going to be taking the average of this term on top over all of my training examples, right? And so now if I take the average log likelihood of my training data, that's simply going to be this average over all of the patterns that I have in my training data of this term, where this term is computed for each pattern that I'm summing over. The first term again is the weighted sum of bits of pairs of bits over all pairs for the pattern, right? And the second term is the log of the sum over all patterns of e raised to whatever. Now the second term is common for all patterns that you're trying to store. It's only the first term that differs from pattern to pattern, right? The way I would train it is using gradient descent. So I've defined this log likelihood term, and I'm going to take the derivative of this log likelihood term with respect to the individual weight terms, right? So if I take the derivative with respect to any specific wij, then over here in the first term, only those terms within the summation that invoke that particular wij remain, right? And so this is simply going to be the sum or average over all patterns in my training data of the product of the bits on either side of the wij, because you have wij times SISJ, right? For each edge, you're multiplying the weight of the edge by the bits on either side. So again, just to give you an idea of what those two terms are, suppose I had a 3-state network, and say I was trying to store 1, 0, 1. The various configurations are going to be 8 of them, right? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. These are the 8 possible configurations of my 3-neuron network. And let's say I'm trying to store this pattern, right? So the first term over here is going to be, let me call these weights A, B, and C. It's going to be A times 1 times 1 plus B times 1 times 0 plus C times 1 times 0. So you're basically multiplying the pairs of bits by the weight, and you're summing over all of the edges for the target pattern. That's the first guy. And the second guy is doing this over all possible patterns, right? So now when I take the derivative with respect to, say, this A, only this guy is going to remain because these two don't have A. And the specific derivative is going to be the product of these two neurons, right? And so you get the first term, if you take the derivative, is this product, is the average over all the patterns you're trying to store of the product of the 2 bits on either side of the weight that you're trying to compute the derivative for. What's the second term? The second term is the derivative of the second of minus of log of E of, right? Whatever. Wait, no. Summation over all patterns of exponent of minus of S, right? So you're basically summing the exponent of the energy for all of the training patterns, or all of the patterns the network can represent. And then you're taking the log of that. If you just work through the arithmetic, here's what it comes out as. If I have summation over S x of summation Wij S prime I S prime j, and if I take the derivative with respect to, say, Wij, the first thing that happens, there's a log, is because I have a log, this entire term ends up in the denominator, right? So that gives you that first term outside because of the log. And then the second thing that happens is that now I take the derivative of, so it's 1 over summation times x of whatever. So the next thing that happens is I've got to take this derivative of this guy with respect to Wij. And when I take the derivative of that, it's going to be the x guy will stay, and then you have the derivative of the argument of the x with respect to ij, right? For, if I look at this one, everything to the right. So when I take the derivative of an exponent, it's going to be exponent times the derivative of the argument, right? And so I'm being lazy, but you get the idea. So that's basically what would happen. I'm going to have this term within the log come to the denominator. Then I'm summing over all possible states. For each state, I'm getting this exponent term. And then I'm getting the derivative of the argument of the exponent with respect to Wij, which simply leaves me with S prime I, S prime j. If I rearrange that, then I can write this as summation over all S prime, and I just move the denominator in, right? So these two guys are the same, times S prime I, S prime j. And if I work that one step further, that term over there is simply the product of the state S prime, the probability of the state S prime as defined by our Boltzmann equation. So that simply becomes the derivative of the of log of this ugly sum simply becomes the sum over all possible states of the probability of the state times the product of S prime I and S prime j. And that thing is just an expectation, right? And so the second term in our derivative over here, we are really speaking of the derivative of this term, simply ends up being the expected value of SI over all possible states. Unfortunately, we have an exponential number of these states, so you cannot explicitly compute this expectation. And when we want to compute an expectation over a very large space, and we cannot do it analytically, then what is the standard approach we use? We will sample, right? And so what we're going to do is the expectation can be obtained as the average of samples drawn from the Boltzmann distribution. And then the question is, how do you draw samples from a Boltzmann distribution? And the way you draw the samples from the Boltzmann distribution is simply, I can just initialize the network and let it evolve. And after a while, I can take a snapshot. And whatever snapshot I get is going to be a sample from the distribution represented by the network. So initialize the network randomly, let it evolve by probabilistically selecting state values according to the logistic as we first saw. And then after many epochs of this evolution, take a snapshot of the state. I'll call this a simulated state, simply because it's a sample, right? If I repeat the process many times, I'm going to get an entire collection of these simulated states. And now, if I want to compute the second term in my derivative, it's the average of the product of the states over all the product of the pairs of bits over all the states that I have obtained by drawing samples in this process, all of these simulated states. And so the overall maximum likelihood training basically just ends up looking like this. The derivative of my log likelihood with respect to any wij is simply going to be the average of the bits of the products of the bits on either side of the connection for all of the training samples. The first term is over all of my training samples, right? Minus the second term is the average of the same pair over a large number of samples that I have obtained by simply letting the network freely and taking snapshots. So here's what the mechanism would be. I initialize the weights, let the network run to obtain simulated state samples. That's going to be my gradient given by the formula on top. I compute my gradient and update my network, right? And if I keep doing this, eventually I'm going to get a network where the probability of my training samples is going to be high, and the probability of training on samples that look like it, samples from that class, and hopefully the probability of out of sample states is going to be low. Now, if I look at it, this basically is the same as the update rule for the Hopfield network, right? We just went through this entire mathematical explanation, but it turns out that at the end of the day, we basically end up with the same update rule that we had for the Hopfield network, which we fully understand, even without all of the complex math. And so basically this first term is going to be the term that computes the minimizes the energy of my target pattern, and the second term in my gradient is basically pulling up the energy of all of the patterns that are not target patterns. And then once we get there, we get all of the same tricks as before. We don't need to sample many things. You can just sample in the vicinity of the current of the patterns we are trying to store, and the various other tricks that we saw will still hold. So what this means is that the difference between a Boltzmann machine and a Hopfield network is basically minimal. The Boltzmann machine is basically just the same as a Hopfield network, except that when you want to let the network evolve, the evolution is stochastic rather than deterministic. With that one change, nothing else changed in the entire process. Right? Now, I'm not going to ask you polls or questions. I know you guys are tired, so am I. But I think this whole thing makes sense. Now, let's go to the other topic. the network can store up to n-bit patterns. We saw this for a Hopfield network, right? But how do we increase the capacity of the network? We saw that to increase the capacity of a network, I can add a large number of neurons whose values I don't really care about, right? And so now, if I want to store like a million 10-bit patterns, I'm going to augment my 10 bits. Well, I don't have a million 10-bit patterns, but I can, let's say 100 10-bit patterns. If I want to store 100 10-bit patterns, then I can augment my 10 bits with 1,000 other bits. And so now these become 1,000-bit patterns. And we know it's easy for us to store, much easier for us to store 1,000-bit patterns than it is to store 10-bit patterns if you have a small number. So that's basically what we're going to do. But then when we read it, we're going to ignore the remaining 990 bits, and we're going to only read the first 10 bits. So if I augment my data with n-bit data with k bits, I end up with a network which has n plus k neurons, and the capacity of the network is n plus k. Although we only care about the pattern of the first 10 neurons, right? Because we're storing n-bit patterns. And so this was the terminology. I augmented my data by adding a whole bunch of bits. But the ones I'm really going to read are the first n bits. These are what I call my visible neurons or visible bits. And the remaining bits, which are somewhat uninteresting, but are only used to increase the capacity of my network, are what we will call our hidden neurons or hidden bits. These can be set to anything in order to store a visible pattern. So if you look at it, for a given set of visible neurons, if I'm augmenting it with k neurons, there are 2 raised to k possible patterns for these hidden neurons. And I can choose any one of these for the visible neurons, right? To extend my visible neurons. So which one do I choose? Ideally, I want to choose the extension for any visible pattern such that the extended pattern has the lowest possible energy so that it maximizes the probability of recovering that particular visible pattern. But that search space is an exponential search space for any given weight, right? And there's this trick. Which pattern has the lowest energy depends on my weights, but the weights itself depend on the patterns I'm trying to store. So there's a chicken and egg over here as well. So we have to deal with that. But then we also have this additional factor that we could in fact have multiple hidden patterns coupled with any visible pattern. So that would mean that these are multiple stored patterns that all give you the same recall for the visible patterns, right? And so how many do we permit? Can I just say that for this 10-bit pattern, I'm going to augment it with 100 bits, and I'm going to do it once, or I'm going to do it 10 times, or do I need to assign a number? Or alternately, could I just consider every possible way of expanding my 10 bits to 100 bits? And when I'm speaking of every possible way, what exactly do I mean by saying that I'm considering, when I'm expanding 10 bits to 100 bits, there are 2 raised to 90 possible ways of expanding it, right? What do I mean by saying I'm going to consider all of them? To see that, let's go back and look at our problem again. This basic framework has no hidden units. We are extending it to have hidden units. But now, with the hidden units, the complete state pattern for even the training patterns is unknown because the training patterns are only defined over the visible units. But what are you really interested in? If I go back and look at it in terms of probability distributions, and I'm performing maximum likelihood estimation, go back and remember what we said when we were discussing EM or variational autoencoders. Your maximum likelihood training is maximizing the likelihood of what you observe, right? So you want to maximize the likelihood of the visible bits, the one inside the blue circle, for the training patterns. You're not really interested in what's happening over the gray bits, the ones that are not colored. So in other words, an extended pattern S is going to be a concatenation of my visible bits and my hidden bits, right? but I want to maximize just the probability of the visible bits, P of V, not P of S, because that's all I really have in my training data. And so I must maximize the probability of P of V, which is given by summing over all possible hidden patterns, right? So the probability of any visible pattern is going to be summing over all possible hidden patterns. So you'll be considering all patterns where the first V bits are the pattern you're interested in, and you're going to have 2 raised to k such things. So you would actually be, you're computing P of S is P of V comma H. You're marginalizing out H. So you're summing over all possible H. That gives you P of V, right? And this is what you're going to be maximizing. So if I go back and look at my network, I have the probability of S was given by the Boltzmann machine. The probability of V is summing the probability given by the Boltzmann machine over all values of H, all possible settings of the hidden bits. And so I must, which basically, so the probability of any visible state sums over all hidden states. So now when I perform maximum likelihood training, the thing changes. So here the probability, log probability of a particular visible pattern is given by this guy here. The probability of the visible pattern is given by this guy over here. So there's a log outside. And this summation basically will occur in the numerator, right? It's not going to occur. The denominator is common to all of them. And so if you look at that, it's going to be the log of the summation over all hidden patterns of the exponentiated field over all extended patterns with that particular combination V. So minus, of course, the same denominator term that we had earlier. So the difference between this guy, and what we had earlier is that over here inside, we have a summation in the numerator because you're summing over all possible hidden pattern values for any given visible pattern, right? And then once again, when I want to perform the maximum likelihood training, I'm going to be trying to maximize the average log likelihood of the data that I've been given, my training data, which is basically the average log likelihood of the visible patterns that I have been given, the patterns of visible units that I have been given as part of the training data. And if I just take a derivative and work through this, it turns out that now again, earlier, for the first term, you just simply had log of this exponent, and the log and exponent canceled out, right? But now once I include the hidden units, there's a summation within the log, even for the first term, both in the numerator and the denominator. But as things turn out, it turns out that if you just work through the arithmetic, basically what you get using exactly the same arithmetic as before, you get that the derivative of the log likelihood with respect to any parameter wij is the expected value of the product of two products of pairs of bits, where the expectation is taken over the probability distribution of the hidden states, the hidden bits, given the visible bits, right? So it is the expectation of taken over P of S given V for the first term, and the second term is the same as what we had before. Now, what is this first expectation? Again, that first expectation is not characterizable. We don't know what the probability distribution is, but we know how to approximate that expectation by sampling. And so what the whole thing is going to be is that even that first bit is computed as the average sampled hidden state with the visible bits fixed. That's this one. And the second one is the average of the products of bits over all possible samples drawn from the distribution. And so if you just work the arithmetic out, I mean, if you sort of look at how the whole thing gets implemented, you want to maximize the marginal probability of V And this requires summing over an exponential state space over all of the hidden bits, which is not feasible. So we use simulations. So here's what I do. For each training pattern V, which is just the pattern of visible bits or the observed bits, I'm going to fix these neurons and let the network evolve. So again, the question we asked is, what must be the hidden values? How do I extend this visible bit pattern, right? After working through the arithmetic, what it turns out is, in order to find out what is the best setting of the hidden patterns, the best thing to do is to let the network decide. You fix the visible bits and let the network evolve, but only the hidden bits are updated. And eventually the hidden bits are going to converge to some value, right? So to some distribution, you can take a snapshot from it. And when you take a snapshot, now you can compose an extended pattern that you're trying to store. You repeat it many times. So for each visible pattern, you can repeat this simulation many times. Each time you're going to get a different snapshot of H. Each of the snapshots is going to give you a different extended pattern. This collection is now going to be your training patterns. So for each visible pattern, you will get many different extended patterns, where for each extended pattern, you just fix the visible bits, let the network evolve, and then read off the hidden bits, right? And so that's going to be, these are the patterns you're trying to store. And then, of course, for the second term in the denominator that in the gradient that we had, we wanted to let the entire network evolve. So here, we let all of the net bits just run freely, right? And then after the network has evolved for a bit, you take a snapshot, and you can repeat this process many times. So the overall process is this. For each training pattern, if I'm doing something like SGD, when I'm doing SGD, I'm going to be updating the network for one training pattern at a time, right? So for each training pattern, I'm going to be fixing these bits to the pattern that I'm trying to store. I'd let the network evolve, but only this portion of the network. And then after a bit, I'm going to get a snapshot. And that's going to give me an extended pattern. I could do this more than once, or I could do this just once, right? And then that's going to give me a complete extended pattern. Then after that, I will sort of let these guys evolve too. I'll unclamp these bits and let the entire network evolve. And when the entire network evolves, after a bit, I'm going to get it's going to settle at some distribution. I can take a bunch of snapshots, and those are going to give me my the snapshots over the entire distribution, right? And so now the average of the pairs of products over all of the patterns that I got when I clamped the visible bits, minus the average that I got when I just let the entire network evolve, this is going to be the gradient that I use to update my network. So basically the overall process is you're going to initialize all of your weights. Then you go over your training bits, sample patterns. For each training pattern, first you fix the visible bits, let the network evolve, and then take a snapshot. Then you release the visible bits and let the entire network evolve and take a snapshot. And the difference between the outer products of the states in the two cases is going to be the gradient that you would use to update the network. Very simple. So this is your Boltzmann machine. It's a stochastic extension of Hopfield networks. It enables the storage of many more patterns than Hopfield networks, but it also represents a probability distribution. It's a generative model. So if I train this network using, for example, lots and lots of examples of faces, you would expect that once the network is trained, if I let the network run and I took snapshots, it's going to give you face-like images. It's a generative model, right? So now, this is again the training procedure. So training, given a set of training patterns, initialize the weights, then fix this guy, let these things evolve according to this equation, take a snapshot, then unclamp this, let the entire network run according to this update rule, and then just the difference, and take a snapshot, and the difference between the two outer products is the gradient that you'll use to update the network. Once the network has been trained, then you can go back and use it for things like pattern completion or denoising, the two examples that we saw, right? So for pattern completion, if I know, for instance, if I know these 2 bits and I'm trying to complete the pattern, then I'd fix these 2 bits. I say this is going to be 1, this is 0. They can never change. And I just let the network evolve and let these bits and all of these bits evolve. I'd run, and after a while, I'm going to take a snapshot. I can repeat this many times and then take the average of these bits over all of the snapshots to give me my new reading for these bits. So I can use this for filling out patterns, denoising patterns, computing conditional probabilities of patterns, but we've been speaking in terms of storing information and completing patterns, right? But it turns out that this network can also be used for classification. So Boltzmann machines and Hopfield networks are basically the genesis of a lot of what we do in neural networks today. Now, how would you use a network of this kind for classification? Can anyone guess? Anyone?
Compare to closest saved pattern.
For the class, actually, it's even simpler than that. Here's what I would do, right? I'm going to extend, for classification, you're given a class and a feature, right? I can represent the class as a one-hot or even a binary vector. And now I just extend my pattern by attaching the class bits to my feature bits. So earlier so if you were training, in your conventional training, you might have something like, a feature which says 1, 0. I'm just assuming it's a binary feature. It doesn't have to be binary. And then you say cat, right? But your cat has some binary representation, say 0, 0, 1, right? I can just call this whole thing an extended pattern, where these were the feature bits and these were the class bits. And then I can just go ahead and train my network. And now, when I'm performing classification, it's like saying these bits were not given and these bits were given. So I can just give you these bits, let the class bits evolve, and then read off the class. So the whole thing can just be used for classification. Given features, anchor the features, and you can estimate the posteriori probability distribution over classes, right? Yeah.
What happened to a feature that we haven't seen yet? Is this network guaranteeing that if this feature is close to a feature that has been seen, then
you're assuming that the Boltzmann distribution actually captures that distribution, right? We said this is a generative model. So if I train it on faces, it should be able to generate not just the faces you gave it in training, but also generally images of the class of faces. So under the same concept, you can say, think of features that you have not seen are probably noisy versions of features that you have seen. And so they will be in the same bowl. Okay, right? So issue is, this is where a lot of the work on neural networks began in the 80s. And you can find a lot of nice papers on this topic by Hinton, in fact, done from here at CMU. The problem is it takes forever, right? It's a stochastic network. Every time I give you something, there's a whole lot of simulation. You're taking a machine, you're letting it run for a long time, you're taking a snapshot, then you're letting it run again for a long time, you're taking a snapshot. This is not going to be amenable for doing anything useful or practical with more than a few bits. You can imagine that training ImageNet using this procedure is going to kill you. If it doesn't kill you, it'll kill the Amazon forest. It'll burn the earth training your first network. We don't want to do that. So we come up with approximations. The one that really works is the restricted Boltzmann machine. Now, when I looked at, when I showed you this figure, in this figure, we're just using the extended bit pattern as a full bit pattern and just training a regular network, right? It's still a loopy network where the hidden neurons connect to the visible neurons. Every neuron connects to every other neuron. I can add a restriction which says that the visible neurons don't communicate with one another. So unlike over here, where I actually have these arrows, and I have these 5 neurons all connecting to one another, and I have these k neurons all connecting to one another, I'm going to say that within the left-hand side, the neurons don't talk to one another. The visible neurons only talk to the hidden neurons. The hidden neurons only talk to the visible neurons. They don't communicate with one another. When you do that, the network becomes like this, right? Those are the hidden neurons. These are the visible neurons. There are no connections between the visible neurons. How does this help? Turns out that this makes the computation far, far, far simpler. This is called the restricted Boltzmann machine. It was originally proposed as a harmonium model by Paul Smolinski over in Johns Hopkins, I think. So think about it this way. It's still the same approach, right? Every neuron gets a field, and its value is flipped according to the field. Now, over here, when I was training the network, I fixed the visible neurons, right? And then I could let the hidden neurons evolve, and the hidden neurons would evolve and evolve and evolve and evolve, because any hidden neuron value affected the field at other hidden neurons, because the hidden neurons were connected to one another. If I remove the connection, then something interesting happens. What happens is that the hidden neurons no longer connect to one another. So when I set the visible neurons, there's only a one-step process to read off the hidden neurons. The fact that the hidden neuron, a specific hidden neuron was set to a value 1, doesn't change the probabilities at the other neurons. So there's no further evolution. It's a one-step process, right? And so what we can do is that over here, I can just give it the visible neurons, and I can just read off the hidden neurons in one step. I don't need to net the network evolve. But that's only for the numerator terms and the first term and the derivatives. For the second term, we still needed to have the entire network evolve, right? Both the visible and the hidden neurons. So there we still have an issue, but then you also get there are still things you can do over there. So here's how it works. For each training pattern VI, you would no longer have those connections, although I've drawn the connections between the hidden neurons, right? So now in the full Boltzmann machine, this is what we had. Every neuron connected to every neuron. So you'd fix the visible neurons, let this thing evolve for many, many steps and take a snapshot. Then you'd unclamp the visible neurons, run the entire network evolve and take a snapshot. Over here, I'm going to, in this case, I just anchor the hidden visible units and then just sample the hidden neuron once. There is no looping, and I'm done. So for the first step, the compute basically disappeared. Now, in the second step, over there, we unclamp the visible units and let the entire network evolve several times to generate these samples. We are still going to have a similar procedure, but then the computation is much simpler. You'd have the visible units. From these visible units, you're going to just sample the hidden units. Then you fix the hidden units, and then you go back and re-estimate or redetermine the visible units, because you're letting the entire network evolve. Then given those hidden visible units, you go and sample the hidden units and keep repeating this process. So the way it would work is that you'd fix your visible units. From those, you'd read the hidden units. From those, you'd read the visible units. From those, you'd read the hidden units, and so on. And now, when you compute the derivatives, the derivative is simply going to be this. The derivative, the first term in the derivative is going to be the outer product between the complete state vectors, right, of the complete state vector with the visible units fixed, right? So that's simply going to be the product. That you only have connections between these guys and these guys. You don't have connections between amongst the visible units or amongst the hidden units. So the very first snapshot that you took over here, in that snapshot, the derivative of the weight connecting any visible neuron to any hidden neuron is simply going to be the product of those two neuron values. So for any given weight, the first term is the contribution to the derivative of the weight is simply the product of the two neurons at the first iteration. And then for the second guy over here, you need the same product, but then computed after the entire network has evolved for a very long time. Now this is still slow, right? Because you have to keep going up and down and up and down. So, Again, remember, for the Hopfield network, there was no need to raise the entire surface or even the entire valley. We just wanted to raise the neighborhood of each target memory after evolving for a few steps, so that I can do the same thing over here. I can take the visible neuron, compute get a snapshot of the hidden neurons. From the hidden neurons, I can get a snapshot of the visible neurons. And then from the visible neurons, I can get a snapshot of the hidden neurons again. So it's just this computation. And then on this one, I can simply compute the difference between the product of these two neurons here and the product of the two neurons in the next round. And that is going to give me an estimate of the derivative of the log likelihood with respect to that particular weight. And I can use that in my gradient descent for each training instance. And now with this snapshot, with this modification, this entire Boltzmann machine becomes a very simple and very easy model to actually train. But then when I look at it this way, what does it look like?
MLP?
Looks like a 3-layer MLP, right? With a very, very restricted kind of training paradigm. That's basically what it ends up being. So RBMs, it turns out, are excellent generative models for binary or binarized data, but then you can also extend them to continuous value data. We're always speaking of bits, right? We're saying every value is 0 or 1. We can do that with, we can make them continuous valued by saying that at the visible units, you don't compute just a bit, but you compute the mean of a Gaussian or some parameters of a distribution. That's like having an MLP with non-threshold activations or non-sigmoid activations. That's basically what it becomes. The entire model can still be extended in a very simple way. And it turned out that neural networks are not very popular for training for pattern classification tasks till the early 2010s. In fact, in the early 2000s, if you submitted a paper to NeurIPS, what was called NIPS then, and then if your paper title had neural network in it, they would throw the paper out without even bothering to review it. It was anathema, right? Because the whole area was generally considered somewhat of a failure. Things didn't work. There was only one man in the world, or maybe a small number of people, who continued very bravely, chugging along, Hinton being one of them, because the field itself was his invention. And amongst all of the various things he tried, he eventually realized in around 2005 that when you want to train a network, what really happens is that the network gets stuck in bad local minima, which is why these things don't work, particularly when you have insufficient amounts of training data. So he came up with this idea that you can just train the network as a Boltzmann machine. And Boltzmann machines are easy to train. So now the weights that you got from the Boltzmann machine, those could be used to initialize the final training of the network. And it turned out that doing that made all the difference. Things that got stuck in really bad local minima suddenly began giving you lovely classification. And so that was really the beginning of the new neural network revolution, where it became not only acceptable to have neural networks in your title at NeurIPS, now it's gone the other way. If you don't have it, your paper gets thrown out. Anyway, so there were these extensions where you could go from Boolean values to continuous values. Then of course, there are other things you can do. You can make these were called, there were variants called Helmholtz machine, deep Boltzmann machine, where the network, you can think of this very large collection of neurons, except now the neurons are not just organized into two sets, they're organized into many sets, which just locally talk with one another. And then once you do that, then the training algorithm once again must be updated accordingly. All of these are various variants on the basic model itself. There are various other algorithms for learning and inference using these restricted Boltzmann machines or deep Boltzmann machines, which can be used for feature extractors. They can be used for generative models. They can be used to create more structured deep Boltzmann machines and so on. I'll stop here. I would have loved to say I'll take questions, but I don't think any of you is interested in questions, so I'll let you go. This is the last lecture of the semester, but given by me. There will be a guest lecture on Wednesday, which I highly recommend everybody attends. Thank you. Thank you. I'll take questions if you have any, but I don't think you will. I think everybody just wants to go back home and sleep.